Okay, so we're so excited to have you here. I want to welcome you again to Flatiron School's You Had Me at Linear Regression. My name's Catherine Sommerfeld. I'm the Director of Marketing Campaigns and Events here at Flatiron School. Part of my team's job is hosting free introductory workshops like today's event to give you the opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. Again, a quick reminder, we'll be using the chat as our main source of communication, so make sure to set that little blue button from host and panelists to everyone so we can all chat together. Without further ado, I'd like to introduce our guests for today. Alyssa is here representing our admissions team, and she will be in the chat with me as we're going. And Greg D'Amico is here representing our data science team. So Greg, go ahead and take it away.
All righty. Thank you, Catherine. Appreciate the intro. Glad to see all these names out there. Welcome to this event. I'm going to drop a link. First of all, this is just a link to some Google Slides that I will be following. So quick sort of outline of today. I'm going to go over these slides for about half the time, 20 minutes-ish, something like that. And then I want to go over a little bit of code. So don't worry if you're new to Python. This is going to be some fairly elementary code, and I'll be sharing the code with you as well. It's on a public repository, so I will drop that link as well when we get there. Okay, so let me share my screen and we'll get started here. Okay, so you had me at linear regression. Really what I want to do is just, well, obviously talk a bit about linear regression. It turns out that this is an extremely powerful idea, and it's one that we tend to use and reuse all the time in data science. And in fact, we often will sort of augment it or add some bells and whistles to it. And it can be an extremely flexible tool as well. Okay, so we'll sort of get a peek at that, but we want to do a sort of straightforward, simple version of this just to make sure that we know what we're talking about here. Okay, so what is linear regression? Why linear regression? This is really one of the fundamental tools in a data scientist's kit. If you're interested in going on and studying data science or statistics, you will almost certainly encounter this tool, and it's incredibly useful. You will find it to have all sorts of applications. Now, it can be done in what I like to call a couple different modes of statistical work. So you might be working in a kind of inferential mode. And what I mean by that is, if you're working in an inferential mode, you are trying to gain some knowledge. You're trying to learn something about some variables, some data that you have in front of you. And so one thing that linear regression can be used to do is to try to get some understanding about how one variable relates to another variable. Right? This is sort of the fundamental idea of linear regression. But that idea that I can use one variable to learn something about another leads to a different kind of statistical work, what we might call a predictive mode of statistical work. And in that context, what I'm trying to do is I'm trying to use one variable in effect as a proxy for another, right? Maybe what I want to have is some predictions, some guesses about the value of some variable, given the values of some other variable. And the idea is, well, if I just had a sort of model, right, I could plug in the values of the one variable and get some estimates or predictions about the values of this other variable that I'm really interested in, right? That is an extraordinarily powerful idea. It is, in effect, what machine learning is all about. If you go on into some advanced work of machine learning, you will encounter all sorts of different models. I'm going to talk a bit about that in a moment, but linear regression is one of those standard sort of introductory models that you'll probably start with. So a bit about linear regression in particular. What does it look like? I just used the word model. What is a model? Well, we'll say a little bit about what a model is, but in effect, what I'm trying to do is I'm trying to represent some part of the world, right? That's what a model is. It's a representation. So for example, Newton represented gravity as this force that pulls all massive objects together, right? And that was an incredibly fruitful idea because there are massive objects everywhere, right? And so Newton's gravitational theory, you can think of that as just a bunch of models, right? It describes the action of a pendulum. It describes the action of the moon on the tides. It describes apples falling from trees and all this stuff, right? And in effect, you can think of the theory as just this collection of models. Now, in this very particular context, our models are lines, right? We'll say what we mean by that more precisely in a minute, but in effect, what we mean is that when we're doing linear regression, we're building models, and those models are straight lines, okay? Now, the regression bit, you will find if you go on to study more statistics that this term regression, this actually gets used in a couple different ways. And it's not always obvious what is meant by this. One useful way of thinking about it, at least in the context of data science generally, is, well, regression is a type of scenario where the model that I'm trying to, sorry, the variable that I'm trying to model is continuously valued, right? And that's, of course, what makes it appropriate to use a line in the first place to model it, right? If I can have a variable, some variable of interest I want to get predictions for, and that variable can have any value in a long range, right? Some continuum of values, that's going to be what's called a regression problem. In the history of linear regression, the word regression actually comes from another phenomenon about regression to the mean. I'm happy to take questions about that at the end, but it's not really relevant here. But just sort of, that's actually the origin of the name here. And we will also often divide linear regression between what's called simple linear regression and multiple linear regression, okay? And the only difference here is, if we're talking about simple linear regression, then that's just to say that the line we're building, the model we're building, is a function of a single variable. Whereas if we're talking about multiple linear regression, then the line is a function of multiple variables. Okay, that's it. That's the grand difference. Whether you want one variable or multiple variables in your model obviously depends on the context and what you're trying to do. But the same sort of idea that works for single and simple linear regression will also work in the case of multiple variables. Okay. I started to say this a moment ago, that linear regression has sort of this relevance to inferential statistics, but also to predictive statistics and machine learning, right? And if you just think about this very generic but useful idea of relating one variable to another, you can dream up all sorts of possible examples here, right? So for example, as the population density in some city increases, housing prices tend to increase as well, right? That is probably a very natural and familiar phenomenon. More people move to a city, there's more demand for housing. Housing sellers can afford to ratchet up their prices because they know that people are still going to pay for them, right? So here, there's a sort of natural causal story to tell, right? Why is it that housing prices tend to go up when population density goes up? That's not mysterious, right? Other times the relationship is more mysterious, right? And you sort of find yourself wondering, why is it that these two variables are related to each other, right? Sometimes it's because one is a cause of the other. Sometimes it's because there's some third thing that's a cause of both, right? There are all sorts of causal stories or non-causal stories about why variables might be related to each other. But if we're in a sort of more predictive mode, right, then we maybe don't care about the causal story. We just care about the facts of the phenomenon of the relationship. Here's another example. As the number of trees in an area decreases, the concentration of carbon dioxide goes up. Okay. Maybe this is a slightly more mysterious, but if you know some things about trees and how they work, right? Trees are sort of these big absorbers of carbon dioxide. And so in particular, right, when you've got an area with a bunch of trees, you can expect lower levels of carbon dioxide and so on. Here is a simple example. Okay, so this was made in R using a tool called ggplot. And if you look at this slide here, if you look at this picture, what do you notice? Anybody notice anything about this picture? What stands out? Yeah, Keelan says a negative correlation. Good, good. That seems like something that's definitely worth observing. And what are our variables of interest here? What are we seeing a correlation between? Rajiv says weight of cars in US is high compared to other. Yeah, okay, good. That's another thing to notice, right? So you can see that the countries are color coded here. And if you're just looking at our different weights of cars, right, USA tends to have heavier cars. Okay. But Cecily and Rume are pointing out when we're talking about what the correlation is of, we're seeing some correlation between miles per gallon, right, which is represented on the y-axis here, and weight, which is represented on the x-axis here. And as Esther is sort of summing up here, the more the weight, the less the miles per gallon, right? Not too surprising, right? Fast cars, lighter cars tend to, use less gas as they're driving along. Heavier cars would tend to be the more gas guzzlers, have lower MPGs and so on. Okay. Now, notice something else about this picture, right? Is there a sort of a perfect linear relationship between MPG and weight? Cecily says it looks more like a curve. Yeah, it's not a perfect line. We might actually try to represent this as a curve. We could do that. But there's still value in thinking about this as a linear relationship. Maybe we would just cut it off. We could say, well, as long as the car is at least 2,500 pounds or something, there's a nice linear relationship here. Jeff says there's significant standard deviation. Yeah, it's not a perfect fit, right? But what we're going to see is that in a lot of ways, what gives linear regression its power is its simplicity, right? And when you have a very simple model, it's not going to be perfect. It's going to be inexact. But the power is in the simplicity. Right? Dan says 2 lines. Yeah, good idea. So we could try that if we wanted to. We could have one line representing these heavier cars, and another line for the lighter cars. Here's another example of the sort of thing we're talking about, right? What we do when we do linear regression, when we perform or construct a linear regression, right? What are we trying to do? Well, we're trying to build a line, right? We're trying to find a line that passes through our points. And here are our data points spread out. Obviously, the line is not sort of perfectly passing through all of them. They don't lie on a single line. But we can nevertheless have an idea of which line best fits our data points, right? Out of all the possible lines we could draw, given this spread of data points, it turns out that one of them is the best, right? At least one of them is the best, given some understanding of what constitutes a good line, right? Best in what sense? Well, right, we'll talk about this in a moment, but the basic idea is going to be we want to try to compare the points on the line we built to where the actual data points are, right? And if we do that, we can get some sense of how much our model is off the mark, or if you like, error, right? We can get some measure of error. And then we can try to minimize that error by drawing a line that has the smallest amount of error. Okay. Again, thinking about models as sort of idealizations, way back in the 60s, Richard Levins wrote this famous paper about scientific models. And one of the big takeaways from that paper was that there are these trade-offs, right? If we're scientists, if we're building models, we have to be aware of the fact that our models, when we build them, engage in certain trade-offs, right? So one of these trade-offs is between what he called generality and what he called precision. Okay. And so the idea is, right, if I make my model super precise, right, super detailed, well, I'm probably going to be able to get more accurate predictions, but it's going to also be way less general, right? It's not going to apply to as many cases. It might be harder to use. It might also be harder to understand, right? And on the other end of things, if I make an extremely simple model, well, it won't be very precise, right? But it's going to have lots and lots of applications. And so linear regression tends to be on that side of things, right? On that end of the continuum. Linear regression is a simple model. Our models are just lines, right? So there's going to be, in general, there's probably going to be a fair amount of error, but it's extraordinarily simple to use. It's extraordinarily simple to understand, and it can be extremely flexible. There are, of course, in data science, other types of models. So if anybody has done more sophisticated model building in data science, maybe you've worked with neural networks or random forests or these other more exotic types of models, those things, right, while they're definitely more precise, but they are definitely also way more complicated, right? They are harder to build, take a lot longer to train, they are harder to understand, right? So there are these trade-offs, and linear regression tends to be, well, it's simple, so it's going to have some error, but it's incredibly easy to use and understand. One nice way of thinking about this is with maps, right? Imagine that I'm drawing you a map and I'm, trying to send you to some certain place. Well, I could try to give you some incredibly detailed picture of the landscape that you need to traverse. But if I did that, you're probably not going to remember it, right? Or if I draw it, you might not be able to read it. If I just maybe draw, here's a triangle and here's a square and you need to go to the X, that might be good enough, right? And it's simple, so it would be easy for you to use and understand. And, as a model builder, or in this case, a map builder, and what is a map but a model of the geography, I need to make these choices, right? I want to give you a map that's useful and accurate and precise, right? But I have to sort of think about how precise it should be, because the more precise I make it, in fact, the less useful it will probably be. Okay, so let's think for a minute again about these lines, a line as a model, right? Well, if we've taken some fairly elementary mathematics, we know the equation of a line. It looks like, typically this is expressed as y equals mx plus b, something like that. In a data science context, we often change the notation a bit and write it like this: y hat equals beta 1x plus beta 0. Okay, still the equation of a line. I've got something multiplied by some starting variable, some independent variable x. I've got some y-intercept term here, and I put a little hat on the y to indicate that what I'm doing is making a guess or a prediction about what the real value of this other variable y is, right? So y hat, according to my model, the value of y, given some value of x, should be equal to beta 1x plus beta 0. Now, the real value of y is probably not going to be exactly beta 1x plus beta 0. It's going to be a little bit different. Okay. But this is exactly how I construct my best fit line, right? Because what I can do is I can say, okay, well, here's the value that my model is predicting, y hat beta 1x plus beta 0. So pass in some values for beta 1 and beta 0. And then I can compare that with the real value of y. Okay. And if I do that for every single one of my data points, then I can get a measure of error for every one of my data points. And it's useful to square those differences because then they'll all be positive. Right? So I'll have a bunch of sums of squared differences between the y value that my model predicts and the actual y value of the data that I have. Right? And so if I sum up all those squared differences, then the idea would be, let me try to find the line that minimizes that sum of squared differences. Okay. So for example, right, suppose I have these blue data points here. I'm just calling them x values and y values. It doesn't matter what they are, right? This is sort of part of the power and flexibility of this model. Now, if I just look at these lines here, so I've got a blue line here, I've got a red line, I've got a black line. Which of these would you say best fits the data? Any guesses? Got to vote for red. Yeah, red looks pretty good. Another vote for red. I've given this a few times, and usually no one says blue. And if you look at blue, right, the blue looks not so great because almost all the points are above it. Right? Esther votes for black. Yeah, I think the black looks pretty good too. So, in fact, this is a bit of a trick question. So none of these lines actually fits the data best of all possible lines. But of these three here, yeah, I don't know. I think maybe the black, probably the black is maybe the best. Red might be the best. But, we don't want to do this with our eyeballs, right? This is just showing us that we don't really want to find the best fit line by just looking at it. And in fact, it turns out that this is a closed problem. There is a closed form solution to this question about which line best fits our data. We can actually just calculate it. Okay. I will spare you those mathematical details. If you want to explore those, we can certainly talk about them, but there's no real reason to go into that here. Useful. This is the sort of thing that is sort of useful to run through once and never again. Because we have all sorts of powerful software tools that can do this for us. It's good if you understand it and can do it by hand, but it's very tedious by hand. So instead of doing that, let's actually turn to some code here, and we can see what this looks like in an actual example. Okay, so I've got a Jupyter notebook here, and it's sitting in this repository on GitHub. So I will send you all the link right here. And I've actually got the notebook running on my local machine here. So we can just go through this and see what linear regression actually looks like in practice here. Okay. So this is Python code here. And what I'm going to do is I'm going to use a library called Seaborn. Seaborn is first and foremost a plotting tool, right? It's a library for making good looking visualizations and plots, but it also happens to have some data stored inside of it. So I'm going to make use of a data set here. Okay, so I'm going to bring in this package and I'm going to load one of these Seaborn data sets. And this one is called Penguins, because this one happens to be, I'll show you a sample of the data frame here. Right. What I have is information about different penguins. Okay. So you can see I've got various columns here, various different variables that I might try to find some relationship between. This leftmost, well, column, sort of a column here. Notice there's no actual column name here. This is just a kind of index that my software tool supplies automatically here. Okay, but I've got things like species and island. So if you haven't heard of these islands, and I wouldn't blame you if you hadn't, Bisco, Dream, and Torgerson, those are in fact the only 3 islands represented in the data set, and those happen to be Antarctic islands. Yeah, that's where penguins live. They live down in the Antarctic. And I've got a few different species represented as well. Okay, sex of the penguin. And then I've got these continuous variables that have to do with the actual, physical dimensions of the penguin, right? How long is its bill? How deep is its bill? How long are its flippers? How heavy is the penguin? Okay. Notice these are fairly small penguins, right? So we're talking about body mass in grams, 3,000, 4,000, 5,000 grams. So, only, 10, 12 pounds or something like that. Okay, now just as sort of a preliminary step, just to make our calculations a bit easier, I'm going to eliminate any rows that have missing data. Probably it's best to, make sure that we don't have an overwhelming number of such rows before we start. So this line of code here will tell me, okay, well, I'm actually missing just 2 values in the bill length column, just 2 values in the bill depth. Okay, 11 values in the sex column. Okay, but still, this is not a huge number of rows that I would be dropping, so let's go ahead and do it. Okay, this is sort of maximum 19 rows that I'd be dropping. And I've got, let's just actually check to see how many rows I have. So I might run penguins, penguins dot shape. Okay, I've got 344 rows here. So if I lose just 19, and it might be even less than that, that doesn't seem like a big sacrifice here. Okay, so I'm going to drop those rows that have missing values using this very simple command here, penguins drop NA, right? NA for not a value or not a number, null values. Right, so drop all those, and you can see now, right, that these nulls have been eliminated in this new version of the data set that I'm calling penguins clean. Okay, so penguins clean is has no null, no missing values. Cool. Okay, so now, right, remember I said that when we're talking about regression, we're talking about a case where the variable of interest that I'm trying to model or predict is a continuous variable. Okay, so let's just go ahead and pull out those continuous variables. In this case, right, we just saw that those are the ones that have to do with these physical measurements of the penguin, right? 2 for the bill, 1 for the flipper, 1 for the overall body mass. Okay, so here are those columns that I'm interested in: bill length, bill depth, flipper length, and body mass. Also helpfully marked with the units of measurement here. It's nice, millimeters and grams. Okay. And one very powerful function I can use here is called pair plot. And if you look at this function, I'm just going to look at the document string on this function here. Right, you see I can pass in the data. I can actually pass in all sorts of other things. I can decide on a hue that I want to use or a color palette, all sorts of things. And if I read the doc string, always a good idea, not always something we do, but always a good idea, plot pairwise relationships in a data set. Okay, plot pairwise relationships in a data set. By default, this function will create a grid of axes such that each numeric variable in data will be shared, be shared across the y-axis across a single row and the x-axis across a single column. Okay, so basically, give me all your variables. I will plot one against each one against every other one. Now, along the diagonal of this grid of plots, right, that would represent a space where I'm plotting a variable against itself. That doesn't make a lot of sense, right? The diagonal plots are therefore treated differently. A univariate distribution plot is drawn to show the marginal distribution of the data in each column. Right? So on the diagonal, I'm just going to have distributional plots of these different variables. Okay, cool. And in fact, this is all the default behavior. Again, there's all sorts of things I could do if I want some more exotic plots, some variations on a theme here, but this default is going to work perfectly fine for our purposes here. So let's try this out. That is cool, right? This is already a nice visualization here. So you can see I've got my 4 continuous variables here: bill length in millimeters, bill depth in millimeters, flipper length in millimeters, body mass in grams. Okay. And on the diagonal, as was promised, I've got some distributional plots of those different variables. And nothing too surprising there. So we would probably expect something like a normal distribution of these variables, right? Lots of values sort of in the middle, fewer values out at the ends. And that's, more or less what I see here. The plot here for flipper length looks a little bit funny. There's sort of, a strange lack of values right in the middle here, but I also might just experiment with changing my bin size here, and I might get something that looks more normal. Okay. But off the diagonal, right, what I have are these plots, one variable against another. Okay. And because this thing is a symmetric matrix or grid, right, bill depth plotted against bill length, right, well, that's going to look the same as bill length plotted against bill depth. Right, so you can see these two plots here, they're just sort of, one is just a flipped version of the other. Okay. And another thing one might notice here, right, there seem to be actually quite a lot of interesting correlations here, right? And probably it's not too surprising if you just sort of think, I don't know much about penguins, but, right, what would be reasonable to expect about penguins? Probably a penguin that has a really long bill would also tend to have a pretty deep bill, right? Probably a penguin that has a lot of body mass would tend to have long flippers. Okay. Now, there's probably these weird, freakish penguins out there who are really heavy and have really tiny flippers, or have really long bills and really tiny flippers. Those penguins probably exist somewhere, but that would not be what we would expect, right? That would not be the sort of normal, if we may say, not to, make any penguins out there feel embarrassed, but typically, right, these numbers would tend to grow and shrink together. That would make sense. Okay. So let's just choose, for example, let's just choose flipper length and body mass. Okay. I know, body shaming the penguins. I know that, let them not hear this presentation. Here's my flipper length, right? Here's body mass row, flipper length column. So I can see the relationship right there in this plot. Or if I like, I can see this flipped version of it here, flipper length row, body mass column. Okay. And it looks like there's actually quite a tremendous correlation there, right? As flipper length goes up, body mass goes up. As body mass goes down, flipper length goes down. Okay. So we can sensibly talk about drawing a best fit line there. And as a matter of fact, we could sensibly talk about drawing a best fit line no matter what the distribution looks like. But because there does seem to be this, just eyeballing it, linear shape to it, right, we can be pretty confident that the model we build by constructing this best fit line will be a pretty darn good model. Okay. Okay, so let's give this a shot here. The idea is I'm going to isolate the flipper length variable. I'm going to isolate the body mass variable. Okay. And what I want to do is I want to see if I can, in effect, model the second one, body mass, using the first flipper length. Cicely says, how do we handle situations like bill depth versus body mass, where there appear to be two clusters? Yeah, so in a plot like this, yeah. Good question. Now, just knowing what we know about the data, which really isn't all that much, but knowing what you know about the data, what do you think is going on here? Why would there be these two clusters like this? Monica says two different species. Yeah, that's a good guess, right? It might represent a so-called specific difference among the penguins. HM says age, it might represent an age difference. It might also represent a sexual difference, right? So lots of, yeah, Roy says sex, good. Lots of biological species exhibit this kind of so-called sexual dimorphism, right? Where males and females are a bit different from each other. So that definitely could be what's going on here. In human beings, in human beings, there's sort of a moderate effect, men tend to be taller than women and so on. There are, other sorts of species where there are much more dramatic differences between males and females. Other species, there's hardly any difference at all. Laura says, should we have two colors and not just blue? Yeah, that's not a bad idea. So we're just using the default color scheme here. If we wanted to explore build depth and more depth here, I think that might be a good idea. We might try to isolate the one cluster from the other, model them separately or something like that. We could also sort of explore, what if we just take the male penguins? What does that look like? What if we just take the female penguins? What does that look like? Okay. But let's try what we have here. So I'm going to stick with our flipper length versus body mass graph here. So I'm just going to isolate those two variables. And one thing Seaborn can do is it will draw the best fit line if I give it those variables, right? So I have this thing inside Seaborn.regression. There's another function called regplot, right? Or for regression plot. Okay, very cool. Plot data and a linear regression model fit. Okay, let's give this a shot. Okay, very cool, right? So there's our distribution again. It's the same plot that we had above, although the window size is a little different. But now we can actually see the best fit line here as well. Okay. Notice that there's actually a thin little envelope around the best fit line here. What's happening is that Seaborn is actually using different subsets of the data multiple times. And so when you do that, you're going to get slightly different lines. And so we get a kind of confidence interval, if you like, about the line itself. But roughly, right, this is a pretty thin envelope. So we're pretty confident that this is the best fit line here. Okay. Sweet. Now notice, right, that is a line. It's a line, which means that no matter what value I plug in for my flipper length, I will have an answer. I will have a prediction about what the mass of the penguin is. That's awesome, right? Super wide usefulness, super wide applicability. No matter what value you put in here, I will have a guess about the body mass of the penguin. And if we want to, we can also find out exactly what the parameters, that is the beta 1 and beta 0, the m and the b, the slope and the y-intercept, we can find out exactly what those are. Sadly, we can't just pull them out of this plot, but we can use another tool here. So I'm going to go into a tool called scikit-learn. This is a very useful, very widespread, very popular library for doing data science. And you can build all sorts of models with this library. But in particular, what I want to do is to build a linear regression model, which very helpfully in scikit-learn is called linear regression. Okay, so I'm going to bring this tool in, and all I have to do is to instantiate the model and then fit it to my variables of interest here. Okay, so I'm going to take my flipper length, and I'm going to take my body mass, and I'm going to say, hey, give me a linear regression model where what I'm trying to do is to predict body mass given values of flipper length. Okay, and just like that, the code is run, and it's already constructed the best fit line here. And what I can do is I can dig into this fitted model here and grab the coefficient. This is going to be the slope term. and I've also got an intercept term here. Okay, and so if I want to put it into English words here, right, what I'm saying is, here is my model, right? My best fit line is body mass is approximately equal to 50 times the flipper length plus this y-intercept value negative 5,872. Okay. So this is a model I can just carry around with me. I can sort of put this in my backpack, and no matter where I go, no matter what flipper lengths of penguins you present to me, I can pull this model out and say, aha, I will predict that this penguin, whose flipper length you've given me, has a body mass of whatever the calculation turns out to be. Is the best fit line perfectly accurate? No, of course not. Is it nevertheless a useful model of penguin body mass? Absolutely it is. Right? Imagine, not to get too morbid here, but imagine that we later in life stumble upon some, I don't know, some severed penguin flipper somewhere, and we think, gee, I'd really like to have an idea of what the body mass, how big these penguins were, right? Well, if the penguin was from some area that we've studied, right, that would appropriately fit this model here, I could say, well, I can plug that flipper length into my model here and get an answer for you about what we should expect the body mass to be. Okay. Now, notice there are lots of limitations here, right? If I put in, say, 1 millimeter for flipper length, now that's a very tiny flipper, but if I put in 1 for flipper length, what is my body mass going to be? What is my prediction of body mass going to be if I put in 1 for flipper length? I mean, approximately. Yeah, Rumi says negative 5,300, right? It's going to be a negative value, right? That seems kind of ridiculous, right? A penguin can't have negative body mass. I don't care how short its flippers are, right? As long as they're positive anyway. Right, so clearly this model is going to have a sort of range of usefulness, a range of applicability, right? Now, in practice, our numbers, sorry for the scrolling, but our numbers for flipper length were things like, 200, 190, 230. Okay, and when I put those sorts of numbers in here, then I'm going to get out reasonable body masses, things like, 4,000 or 3,000. Okay, so there are definitely limitations to this model, but if flipper length numbers are realistic, then body masses will be realistic too. Rumi asked about this reshape up here. Yeah, so what we're doing here, now there's no normalization going on here. So this reshape, what's happening is that this model, this linear regression tool inside of scikit-learn, it's actually expecting multiple variables. It's actually expecting a multiple linear regression, right? And so what I'm doing here is I'm saying, hey, just treat this flipper length as a single column. So this means, right, reshape it into however many rows it takes to have just a single column. Right? So I'm saying this is my one and only predictor variable. It's got a shape of however many rows, 1 column. Erwin says, why not output the correlation? We could certainly try to find the correlation value as well. Sometimes that's a useful measure, sometimes that's all you care about, right? So sometimes what I want to know is, how useful, how strong is the correlation, right? Sometimes all I care about is just the model itself. I want to be able to make predictions. Right? There are other tools in scikit-learn and other libraries you can use to access those correlation values and so on. But I think for now, I better pause here. So thanks very much for coming. Linear regression, it's a sort of tool that's used all the time because it's very easy to build. It's very easy to understand. And also it's often in some form or another, it's often sort of sneakily involved in building other more complex types of models as well. So really powerful tool. People use it all the time. And I hope this was a nice introduction to it.
Thank you, Greg.
Yeah,
Just want to remind everyone that, oh, we've got a raised hand too. I was just going to remind everyone that Alyssa was here. So if you have admissions questions, please feel free to reach out to her. And Alyssa, can you drop your link in the chat? Thank you. And then we've got a raised hand. Alpha, if you want to drop your question or comment or whatever in the chat or in the Q&A, we can answer it that way. And I just want to say, while we're waiting on that, Greg, I thought that was really awesome, but also thank you to everyone for your participation. Everybody was super engaged, and we love when that happens because it makes for a really awesome event.
indeed.
Oh, okay, no worries. Hit the wrong button, Alpha. All right. Thank you again, everybody. I just want to say thank you for zooming in to join us this afternoon. If you've got any further questions about Flatiron School, Alyssa did drop the link to schedule a chat with the admissions team. She also gave you the information on the data science bootcamp. And as a reminder, you'll be receiving a copy of today's presentation within 3 business days after the event. And if you want to see any of our previous events, you can head over to the YouTube channel and subscribe. Again, thank you and have a great day.